Hello and welcome to Disseminate, the podcast bringing you the latest computer science research. I'm your host, Jack Wardby. I'm delighted to say I'm joined today by Chuzhe Tang, who will be talking about his ACM Sigmod paper, Ad hoc Transactions in Web Applications, the Good, the Bad and the Ugly. Chuzhe is a PhD student at the Shanghai Jiao Tong University. He is interested in database systems and distributed systems, and his research focuses primarily on concurrency control. Chuzhe, thank you for joining us on the show.
Thank you for having me.
Can you start off by introducing your work and telling the listeners what is concurrency control and why is it important for web applications?
So we have web applications, and we know that a web server will typically and most of the time will serve concurrent requests, and those requests, when handling those requests, the application will need to access data resource. Most likely, it is the data in the database systems concurrently. So, in order to ensure that the application is serving the clients the right data and also maintaining the consistency among the data, they need to control how control this concurrent access to the database system. So the mechanism used by the application is called concurrency control. And most of the time when we talk about concurrency control in the database system community, we are actually talking about the mechanism for coordinating the concurrent access made by database transactions. So speaking of database transactions, it is actually a concept or an abstraction that encapsulates multiple requests to different data items in the database systems. When the client or the application could write a handler for web requests as a database transaction, so the access to the database system will be treated as a single unit of work to the database system, and the concurrent control mechanism by the database system can coordinate this request as if those requests are executed sequentially. While internally they are executed concurrently in parallel, but so that the reasoning of this transaction and of course the web application handlers will be much simpler to the developers, while the performance will be improved by the parallelism.
My next question is, how do applications today use concurrency control? Do they use these classical database transactions, or do they use other approaches?
Well, before I started the project and this paper, I think that my assumption is that this application would just to wrap its business logic into a database transaction and just use them to coordinate the concurrent access. But it turns out that although the applications are using database transaction, but they are also using some ad-hoc construct to coordinate the concurrent access. That's what we call the ad hoc transactions by the title of the paper. And those ad hoc transactions are actually, you can think of ad hoc transactions that are the concurrency control mechanism written and designed and developed by the application developers, and their logic, the code sits among the application business logic. So that's why we call them ad hoc.
Awesome. So how are these ad hoc transactions used in practice? And what was the primary focus of your research and of the paper?
The first question is actually the main focus of the paper. We started the paper because we noticed that there are ad hoc transactions. So we started to survey these applications to know how the ad hoc transactions are used in the real applications. For example, how are they constructed? Are they correct? How are the performance compared to database transactions? And so in terms of how are they used, most of the time they just look like a simplified form of database transaction mechanism, but implemented in the application code. So developers could just explicitly write some locking operations to coordinate this access, which is very similar to the classic two-phase locking protocol.
Sure. So you mentioned that you studied various different open source applications to investigate the usage of ad hoc transactions. which open source applications did you look at?
So we actually looked at 8 different applications. Some of them are maybe familiar with the listeners. For example, the discourse forum. We select them according to the GitHub stars. So they are the most stars applications in different categories, including for example forum and social network. And we have seen many e-commerce applications. Actually, it's quite surprising. Right. We found that we have a Ruby application, Java application, and Python application, and in each category we have a e-commerce application that is the most stars one. So it's quite interesting, I think.
Yeah, definitely. So you covered a wide range of different languages and frameworks and object relational mapping frameworks there. Fantastic. Yeah. So what did you find when you were studying these different web applications, and what do these ad hoc transactions look like in the wild? Can you elaborate on how they differ from the traditional database transaction?
Okay, so the first question is the main findings. So the first one, maybe the most uninteresting one, is that they are commonly used. So we have 8 applications, and in total we have found 91 ad hoc transactions among these applications. In order to show that these applications use them for some critical functionality, we actually categorize those APIs into critical and non-critical. It's quite subjective criterion, but anyway, we find that many of them, like 70 something of these ad hoc transactions, are using API that we consider critical. For example, posting API, the upload API, and notification API of some content-centric applications like forum and e-commerce, and of course the checkout and cart API for those e-commerce application. The other findings is that the construction of those ad hoc transactions are comparing with database transactions. They are quite more flexible. In most of the cases, I think it's simplified. And then we find that those ad hoc transactions are pretty error-prone. Like almost half of them, more than half of them, are actually incorrect, and that we have found some like correctness issues that you could trigger by just deliberately, for example, to add some sleep invocation in the application code, and you just have to browser tab to access this application, and you trigger some error. Finally, we also try to understand the performance of those ad hoc transactions. So we selected some API, actually 4 APIs from different applications, and modify them to use database transactions instead of the ad hoc transaction, and evaluate them in 2 different settings. One is that we have contention, and the other is there are no contention. The point of this evaluation is that to test whether ad hoc transaction might be beneficial in performance to the application. So of course, so the 4 APIs show that they can have better performance in contentious workload. That doesn't mean that they can always improve the performance, but it just proves that it potentially can improve the performance.
So if I'm understanding this correctly, when you did this performance evaluation and you replaced the ad hoc transactions with the traditional database transactions and evaluated the performance difference between the two, are you comparing a correct transaction against a potentially incorrect ad hoc transaction? And is the performance gain not just the benefit of seeing how it might be potentially incorrect at some point?
Of course, we have at least we fix all the bugs that we are aware of when comparing the performance. I think definitely if we look deeper, there might be some more bug in the ad hoc transaction version, but we have fixed all the other ones that we know that will trigger bugs. Actually, for example, when we are trying to build a database transaction version, we remove those, for example, the locking call, and instead we put a transaction begin through the ORM to wrap the whole business procedure. And in that case, when we are looking at why the database transaction would abort in this case, but not in the ad hoc transaction, we find that, there is a new bug.
Oh, wow.
So actually, this will be a very interesting debugging technique that potentially could be used in other places.
But I can imagine the open source developers were extremely happy when you, or maybe unhappy, when you found all of these bugs and fixed them. I can imagine they were very grateful for that. So we spoke about how some of these ad hoc transactions are incorrect. Can we talk about what the root causes of these issues were? Like, what were the common mistakes people were making when using ad hoc transactions?
Yeah, sure. So if I were to summarize the root cause, I would say that it is caused by developer either not knowing the principles or not following the principles of classical database concurrency control mechanisms. For example, many of the listeners probably know about two-phase locking. It actually requires the mechanism to have a growing phase of acquiring locks and a shrinking phase of releasing lock. And a shrinking phase, you could no longer acquire more locks. And of course, all the access to the data should happen within the critical section of the lock. So that is basically the principles of two-phase locking. And when developers are trying to, I think they are trying to mimicking the behavior of two-phase locking, they are not necessarily following these principles. They might, for example, they first read the data, and because they need to, typically in web applications, when you access data by giving the ORM an ID, and the ORM will fetch the whole row into the application, and then the application developer they might decide that, oh well, I can lock the row with some fields or by a lock that is identifiable by the content of the field. And in this case, the read access actually happened outside of the critical section, and it will cause the bug. And similarly, this issue could happen with those optimistic ad hoc transactions.
Nice. So you said earlier on that when you did the performance evaluation, ad hoc transactions under a high contention workload outperformed the classical database transactions. What was the performance gain? Can we have some numbers to illustrate the gains?
Well, we said that earlier that there are 4 APIs that we tested. So, and I think the geometric mean of the improvement is like 1.3 times. And so in terms of why there are performance gain, I think it is because ad hoc transaction, when we in the corrected version, could actually sometimes, for example, they could perform some finer grain concurrency other than the database transaction. We know that the database systems typically have, for example, MySQL, Postgres, they will log the data at the row level. They can use some row ID or just put the log alongside the data. And in ad hoc transactions, we find that, for example, they actually log the data at the column level. So in one case, in a simplified version, let's say, a row have 2 columns, C1 and C2. And when the developer just decide that, okay, we can identify, we have a log that is identified by a string called C1 concatenated by the row ID, and another log is identified by a string C2 and concatenated by also the row ID. So when developer are writing ad hoc transaction accessing different columns of the same row, they could actually use those different set of logs. So those access actually don't block each other, and this could potentially improve the parallelism of the whole application. Yeah, that is one of the reasons, I think. I think the other cases, they are actually ad hoc transactions. They are actually, I think, when they are performed in a coarser granularity, they can, for example, database could just lock every row that is being accessed, but the ad hoc transaction could just use fewer log to provide a mutual exclusion between different ad hoc transactions, because they know the access pattern. Some rows are definitely accessed before the other rows, so they can just knock on the first row using its ID. So the same mutual exclusion is achieved, but fewer logs are required. And in that case, fewer logs, not only fewer logs can of course, reduce the locking overhead, but also avoid the potential of deadlock. I think in some APIs, we find that because there are fewer locks on the database system, and in some cases, that database system just abort because the data logs are acquired in some random order, or there might be some read multiply write operation and some later write when database transaction try to upgrade the log into a writer log, and those concurrent transactions could just block each other and deadlock, and that would degrade the performance.
Has there been any other studies on the use of transactions out in the wild, or I believe this is the first survey of ad hoc transactions, but are there other studies out there on transactions, and how do their findings, if they exist, compare to yours?
So yeah, actually there are, I think, two papers that are quite relevant to this study. The first one is called Faro concurrency control. It is published also in Sigma, but I think it's 2015. Of course, you can tell by the name that Faro concurrency control ad-hoc transaction. They're actually pretty much looking at the same on a higher level. They're looking at the same thing, that how application in their own ad hoc or Faro way to coordinate the concurrent access. And the Faro concurrency control paper actually is looking more specifically into the Ruby on Rails framework and its mechanism in their validation mechanism in ensuring the application integrity. So that paper, that is actually a very interesting paper. I recommend all the listener, if you are interested, please go read that paper. The validation, it is actually different, I think, kind of different philosophy in coordinating the concurrent access. In our paper, the ad hoc transactions that we studied, they are very similar to database transaction. Like I said, they are the simplified version of the database concurrence control mechanism implemented in the concurrent application level. So that means the application developers are actually explicitly coordinating by, for example, using locking or using version-based validation to coordinate those access. And in the concurrency control paper, the authors, they are actually the mechanism is the validation mechanism. It's not the OCC validation, but actually they are validating on the invariance over the data. That mechanism is like, for example, you specify that the data, there should be no duplicate value on this column. So the ORM does nothing when to your invariant. Instead, each time you update something, the mechanism would try to ensure that is this value, for example, pre-existing. So if that is the case, I won't update to the new value. So that will cause the duplicate. So that's kind of a different method in coordinating concurrent access in the application level. But I think the core finding are quite, the high-level finding, I think, is that, of course, they're common and they're usually prone to error. They are not always correct, and we should do something about it.
So yeah, it's very complimentary to your work then. Awesome. So what does all this mean in practice then? So why don't people just use database transactions? What puts people off from using them?
For the majority case, the developer do not use ad hoc transaction because they want better performance, because actually, when we are trying to evaluate this application, we actually found many performance issues that we couldn't scale this application to a higher number of concurrent threads. So there are a lot of performance improvement that could come out from other places of the application. So why do they use this? We don't have a very concrete answer, but I have some guesses. Sometimes developers or the application just couldn't use database transaction because the data is spread across different systems. Sometimes the data it's not just the data, but for example, the more like the abstract resource could be allocated in some external service. You just couldn't use a database transaction to coordinate all this access. We have found some cases that used Redis to store some other data. So in that case, you have to write a log at the application level. So this would be the first reason. And the second one is that I would think using database transaction, especially in web applications, might really just degrade the performance and making the application very hard to debug the performance issue. This kind of is kind of against the claim that I just said that it didn't win for the performance. But actually, the case is that when the developer write the application, they use ORM, so they don't write directly the SQL. So all the SQLs are actually generated by the ORM frameworks. So we find that the ORM framework just generate too many redundant and inefficient queries. And if you put all those queries into a database transaction, and that would just make the database just acquire tons of logs and deadlock, and then degrade the performance. And actually, since you are using an ORM, you couldn't just possibly tell whether or how those queries are generated and where the deadlock causing one are located. So that would be another reason, I think. And for a very minority cases, I think developers are just not aware of that. Aware of the existence of database transaction that could just help solve their problem at hand.
So where do you see this research, these findings having the biggest impact? Who do you think this result or these findings are most relevant for? Who should be listening the closest here?
Several parties that may be interested in this work. First of all, I think those people are researching in database concurrency control. I read a slide like few months ago. It says that I think it's from some people from the CMU. It said that database concurrency control research is dead because no one cares about those research. I think he might have some solid point. For example, he had pointed out that many paper research are researching on optimizing the store procedures, but the applications are not using store procedures. Then our finding, of course, we find that statement is true. But we think at least I think that since the application are using ad-hoc transactions to coordinate the access to the database transaction, I think there is a lot that we can do. For example, like how can we get those applications to use database transactions? Should we, for example, do some to improve our protocol so that those problems that I have mentioned could be solved? For example, performance problem, and maybe some software engineering research that we could help developers to apply database transaction and that diagnose those, for example, data errors. I'm not sure about software engineering research because I think of course, we have found many bugs, and we have shown some. I think it's clear patterns. I have read some paper that just introduce some bug detectors according to some pattern. So since we have some pattern here, maybe some researcher could follow on these patterns to develop some new bug detector for web applications. One of those patterns is that we just mentioned you acquire log after you read the database rows. So that would definitely be, I think, easy to detect. I think it's really I really think developers should really consider more about using database transactions so you don't have performance problems. And even though we have measured the performance difference of ad-hoc transaction and database transaction, I have to admit that the contentious scenario where ad-hoc transaction performs well is actually very kind of extreme. I think compared to real world cases. For example, we have some testing the e-commerce application to simulate contention. We just have some tens of hundreds of clients buying the same item. I don't know if at the same time. That I don't really think that is the normal case for the application.
Sure.
So in the normal case, I think we don't have that much contention, and using database transaction just do not perform very differently from using ad-hoc transactions.
Okay.
So at least developers shouldn't worry about performance that much, I think.
Okay, so yeah, the real world's not that contentious, is what you're saying there. It's only the extremes where you see these benefits. Okay, nice. So leading on from what you were saying there, what do you have planned for future research? Where do you go next with this?
We have one discussion section in the paper that I'm not actually quite satisfied with. I just think that I'm not sure. In general, I think of course, we can build systems to, for example, either provide new abstraction for using transaction, or using some more ad-hoc transaction, but I don't know, better transaction, but not database transaction in the application. We might be able to build some new abstractions, but that would be a very difficult research. And also, I think I'm not planning to do the bug detecting stuff, because that's not what my lab is doing. And I'm actually very interested about for the abstraction that could coordinate access to different systems, access to data in different systems. I think it is actually quite the norm today, because you have relational data, and many applications use some semi-relational data in, for example, MongoDB, and they have some cache in Redis, and they also have some object storage, for example, for video, for images in like object store, and all these storage systems provide different mechanism for coding the concurrent access, and they don't necessarily provide serializable database transaction, and sometimes they don't have transaction at all. And since the application of storing data in different systems, there must be some way to, I think, better coordinate those concurrent access. So the developer don't have to write all the log and unlog operation, and of course also eliminate those bugs.
So my next question is, what was the most? I think I know the answer to this question already, but I'm going to ask you it and I'll see if I'm correct. So, what was the most interesting but maybe unexpected lesson that you learned while working on ad hoc transactions?
Unexpected ones are those, for example, that you can have the rewrite the application code to use database transaction, and then you discover new bugs. That definitely increase our bug reports. But I don't really think that is. I don't consider that that's the most interesting one, because today after the project and after the paper is finished, it's hard for me to tell what is the most interesting part. Looking back at the applications, they're super poorly constructed. Even those most popular one, everyone uses them. For example, I'm not saying that this course is poorly constructed, but it definitely could be improved. And so that is, although I didn't have any expectation of how the code quality of those applications are, but I can tell that some of those applications that is, for example, some e-commerce application, their code is really not that clean, I think.
Right. Yeah. Okay.
But that doesn't count for interesting, though.
No, true. But that's kind of what I was expecting. I was expecting you to say something along those lines. Of, I was surprised by how prevalent these ad hoc transactions are, and how often in these big major applications, so many of them are actually correctness violations, which is always a surprise when you hear that sort of thing.
Maybe in the initial month of the project, I'm really surprised by using ad hoc transaction. But in the end, it's kind of reasonable, because after we find that they are using different storage systems, and for example, the transaction should span multiple requests, and sometimes the inefficiency of the ORM, it's kind of like it became non-surprising to me now that they are using ad hoc transactions.
Yeah. So I've got two more questions for you. The penultimate one is, what attracted you to research database concurrency control in the first place? What attracted you to this area?
In fact, I didn't choose to decide to study in database systems, because that is what my advisor is good at researching. So,
okay.
But in terms of concurrency control, it actually, I started my first project is building a concurrent index structure, and in that process, I learned a lot about the concurrent programming, and like proving your concurrent algorithm is like linearizable. And in that process, I really find the I think the reasoning with concurrency actually fascinating to me.
Mm-hmm.
And later I read a paper. It's not a paper; it's an article published by I think Leslie Lamport on the CACM. I think it's called "Brief History of Concurrence Control" or something like that. And in that case, he really explained how he model and think of concurrency in terms of some distributed process and communication and the happen before relation. And after that, I found, okay, I might continue doing concurrence control research for my PhD.
What is the one key thing you want listeners to take away from your research? If the listener goes away and takes one key point away, what would that be?
For researchers, we really need to look deep into the actual application that our research is targeting on, instead of those like pseudo benchmark TPCC, YCSB, and trying to improve their performance. We need to really look at the application and how we can improve the application. And for application developers, please consider using database transaction. That would save you a lot of trouble.
And I think we'll end it there. Thank you so much for listening, and thank you so much, Chuzhe, for coming on the show. It's been a fascinating talk, and if you're interested in knowing more about Chuzhe's work, the links to his paper and all of the relevant materials we've discussed in the show will be placed in the show notes. Thank you very much for listening, and we'll see you next time.